Hi, and welcome to 10.4a Coulomb's Law 1. Coulomb's Law is basically just like Newton's Law of universal gravitation, but instead of mass, we're talking about charge. So I'll just draw a couple things on the next page here. Like I said, the two laws are pretty similar, and we've covered Newton's Law of universal gravitation in the Unit 6 video. So if you want a review of that, you could look at Unit 6. It's basic. Newton's law of universal gravitation just basically states that any two objects that have mass, so basically any objects that are made of matter, even if it's just a proton or an electron, they're going to exert some kind of gravitational force on each other, and it's equal and opposite. And that gravitational force is directly proportional to the mass of the objects, but also the distance between the two objects. And actually, more specifically, it's the distance between the centers of the two objects. And that relationship looks like this. Fg is equal to, it's directly proportional to both masses divided by the square of the distance between them. And you have this gravitational constant, big G, which is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Very similarly, you have Coulomb's law. So Coulomb's law states that, okay, any two objects that have a charge, so now instead of M, we have Q. Instead of mass, we have charge. So mass and charge are just intrinsic properties of matter. So now we're talking about charge, and they exert not a gravitational force. In this case, we're talking about the equal and opposite electrostatic force. And you might have felt this force before. Again, if you go down a plastic slide and you feel that force tugging on your, like maybe the hair of your arm, you felt this before. Anytime you feel static cling on your clothes, that's the electrostatic force acting on you, because you have a separate charge. So maybe you have a certain charge, your clothing has a certain charge, or that plastic slide does, and that difference in charge creates this electrostatic force. And the closer you put your arm to the slide, the stronger the force is going to be, right? If you move your arm very far away, you don't feel hardly any force. But if it's really close there, you could actually kind of see the hairs on your arm moving. That is, if you have hairy arms like me. All right, but same with your clothes, right? So the formula looks almost identical. The electrostatic force is directly proportional to the charges of the objects. So if this charge is greater, the force becomes greater, right? And it's inversely proportional to the square of the distance between the two objects. If this increases, meaning you move further away, then this is going to decrease because you're further away. And just like we had this gravitational constant, there is an electrostatic constant. So this is the formula that we're going to be dealing with today. So number one says an electrostatic force of magnitude F exists between two metal spheres having identical charge Q. The distance between the centers is R. Which combination of charges would produce no change in the electrostatic force between the spheres? So let's see. We'll take one case at a time. It says, what happens if we double Q on one sphere? So we're doubling Q, and we're doubling the radius here as well. So I'm just going to keep these like this. And just like we did with the universal gravitation problems, we want to try to balance out this equation. So you can't just keep on tripling things and quadrupling things to one side of the equation and then leave this equal sign here and be like, okay, yeah, the force didn't change at all. I multiplied this charge by 1,000,000,000, but that's not going to change the force at all. No, that doesn't make sense. Whatever you do to one side, you have to do to the other. So we put a 2 in the numerator. We better put a 2 on the other side of the equal sign. We put a 2 down here. But remember, the radius is being squared, so you have to do 2 squared. 2 times 2 is 4. So the force becomes 2/4 as great. Or if you reduce that, this is 1/2 as great. 1/2 Fe. So we could write this like this. Or 1/2 F, right? So if F was originally 50 newtons, for A, it would be half of that. 50 times 1/2 is 25 newtons. So that's not what we want. We want no change. So it's not going to be that. So B says doubling the charge on both spheres. So 2 double Q1, double Q2, and you're doubling the radius. So, okay, we put a 2 times 2. We put a 4 in the numerator, and a 2 squared is 4. Oh, 4 divided by 4, that's 1 where I come from. So 1 times F, that's going to make the same force. That's no change. So I'm thinking it's going to be B. But let's double check and see what C looks like. So you're doubling the charge on one sphere, and you're halving the radius. This is an interesting one to do, okay? So now we have 2 in the numerator, and we have a 1/2 squared. If you forget how to do that, it's 1/2 times 1/2, right? When you're multiplying fractions, you multiply the numerator, so 1 times 1 is 1, and then you separately multiply the denominator. 2 times 2 is 4, so we have a 1/4 in the denominator. This is a lot of, like, these types of questions could be a lot of fraction type stuff. So yeah, you have this concept. You have to know how to square a fraction. But now we have this fraction in the, it's like a fraction in the denominator. It's a improper fraction. So let's make it a proper fraction. There's 2 different ways to do it. I was taught you multiply by the reciprocal. So that the reciprocal just means flip that. So you multiply by the flip, and whatever you do to the bottom, you have to do to the top to keep the ratio the same. So that gets rid of this, and you have a 4 times 2. That's going to be 8 Fe. So this becomes 8 times F. But not everybody kind of learns that, oh, multiply by the reciprocal idea. Sometimes people say, oh, why don't you just do keep, change, flip? And I was like, what the heck is keep, change, flip? You keep the numerator, you change the multiplication, you keep the numerator, you change the multiplication, you change the division into multiplication. It's really not that hard of a concept. Keep, change, and then you flip. There's your reciprocal. All right, you flip this guy. This is 4 over 1, and you do the same thing, right? You get the same answer. This is 8 times Fe. All right, so my students like keep, change, flip. You keep that, you change this to multiplication, you flip that guy. All of a sudden, you don't have an improper fraction anymore, and everybody's happy. So, but it's not that. It's 8 times as big. We wanted no change. It can't be number C, but you need to know how to do that. So D says you double Q. You're doubling Q on both spheres while having R. Oops, I got ahead of myself. So this is 1/2 times R. And I already have this over here. So it's 1/2 squared, which is 1/2 times 1/2. So you get a 1/4 in the denominator, and you get a 2 times 2. You get a 4 in the numerator. You give yourselves a keep, you give yourselves a change, you give yourselves a flip, and then that's 16 times Fe. So you could see it's, if you double the charge, or if you double both charges, you get a stronger force if you're doubling both charges, right? But again, choice B is the correct answer because F times 1 is just F, so it's no change there. All right, number 2 is slightly different. So it's the same formula, but it's asking a different type of question. It wants you to calculate the actual force. So it says 2 small metallic spheres, sphere A and B, are separated by a distance of 4 times 10 to the negative 1 meters as shown. So the radius is 4 times 10 to the negative 1 meters. I'm going to move this over because I think I'm going to need some room here. And then it says the charge on each sphere is 2 coulombs. So Q1 is equal to 2 coulombs. Q2 is equal to 2 coulombs. They're both positive. And it says point P is located near the spheres. What is the magnitude of the electrostatic force between the 2 charged spheres? Okay, here's Coulomb's law. Fe is equal to K, Q1, Q2 over R squared. So you got Fe is equal to, you run into your first roadblock. What the heck is K? You look in your reference table. So you look down the symbol column for a lowercase k. Boom, there it is. K is right here. It's the electrostatic constant, which has a magnitude of 8.99 times 10 to the 9 Newton times meter squared per Coulomb squared. That's kind of similar to the universal gravitation constant. This is the number that we were talking about before. But no more. We're talking about K now, the electrostatic constant. So you want to make sure that you write the units somewhere. Oops, 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. We'll talk about why it's so weird. That's a pretty weird unit, right? I'll plug in the units when I write them in here. So we have the electrostatic constant. Even though they're both lowercase k, this is not the spring constant. It's a totally different concept. But I could see why people would be a little bit confused. There's like, oh, I remember lowercase k, and I remember it being a constant. That's the spring constant, right? But we're talking about electric charges here. We're not talking about springs. All right, so this is 2 coulombs. This is 2 coulombs. And now we have the radius, the distance between them is 4 times 10 to the negative 1 meters squared. I wrote the units in here on purpose so you could see something. We want to get a force, right? So our force is going to be in terms of newtons. So we better get an answer in terms of newtons. And there it is. There's the Newton. But what happens to the other guys here? Well, we have a Coulomb times a Coulomb. A Coulomb times a Coulomb is a Coulomb squared where I come from. And you have a Coulomb squared in the numerator here. That's going to cancel with this Coulomb squared in the denominator of the units of the electrostatic constant. Now, in the denominator, you're squaring a distance. So you end up with a meter squared. And you have this meter squared here. That cancels with that meter squared there. And you're left with an answer in terms of newtons. So that's kind of why the units are kind of weird. All right, so you do this multiplication, and you make sure that you show your work in your calculator. I just want to show you how I do it because I use that E button and the capital E button where it's like this double E idea over here. I don't know what that was. Hold up. All right, that capital E button is just, it's the scientific notation button, right? So it means times 10 to the. And your calculator recognizes that as scientific notation, so you're not going to run into any problems with PEMDAS. All right, so you do second E 9. That's an 8.99 times 10 to the 9. Times 2, divided by, so you close the parentheses for the numerator, divided by, and I kind of get paranoid with, I put double parentheses here because I'm going to do 4e negative 1, close that parentheses, square it, close the parentheses for the denominator. You probably don't need to put all those parentheses, but I just like to be better safe than sorry. And you get 2.25 times 10 to the 11. 2.25 times 10 to the 11 newtons of force. That's the answer there. Now, that's a lot of force, but you have 2 whole coulombs, and they're relatively close to each other. 4 times 10 to the negative 1 meters, that's about 40 centimeters away from each other, so just over a foot. All right, number 3 says 2 conducting spheres are separated by a distance of 2 meters between their centers. Sphere A has a charge of 3 times 10 to the negative 4 coulombs, and is repelled by a sphere of a force of 2.5 times 10 to the 2 newtons. What is the charge of sphere B? So you write down your given information. Don't forget to write down K as well. And then you write down what they're looking for. You're looking for the charge of the second sphere. Oops, Q2. All right, so you write down Coulomb's law. Fe is equal to K, Q1, Q2 over R squared. And then at this point, you could plug in your numbers. So you have 2.5 times 10 to the 2, 8.99 times 10 to the 9, times 3 times 10 to the negative 4. You're looking for Q2. You divide by R squared. So this is 2 squared. And then you could like cross multiply or multiply both sides by 4. And you get an answer of 1000 is equal to 2.697 times 10 to the 6. Gets real sloppy times Q2. And then you divide both sides, so 1,000 divided by 2.697 times 10 to the 6, and you get a charge of 3.7 times 10 to the negative 4 Coulomb. So pretty much almost the same as your first charge, just slightly different. Now this gets a little hairy. I mean, you have all these scientific notations here. You have a division with the square, and you're plugging in numbers, and then you're trying to solve for Q2 with all this stuff. Some people think it's easier to solve for Q2 first, so I'm going to erase this stuff here. And now let's do the same math, kind of, but we're doing the math with the variables. We're not going to actually do it with numbers. And then when we get an equation for Q2, we're going to solve for Q2. Well, then we'll plug in the numbers, and we could just do it all in one shot in our calculator. It's the same thing. I mean, if you are not comfortable doing that, just watch this anyway. Maybe you like it. So you cross multiply or multiply both sides by r squared, and you wind up with k Q1 Q2 is equal to Fe times r squared. That looks like a V. There we go. And remember, our goal was to solve for Q2. That's what we're looking for, right? So let's keep solving for Q2. You divide both sides by K Q1, divided by K Q1. So Q2 is equal to Fe times r squared over K times Q1. And now we have an equation for Q2, which is nice. And now we could plug in those numbers. So this is 2.5 times 10 to the 2 newtons times 2 meters squared, divided by 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. And then this is 3 times 10 to the negative 4 coulombs. And you get the same answer. So that's just another way to look at it. Either you plug it into the equation first and then you solve, or if you like, you could solve for Q2 first and get an equation, and then you plug in the numbers and you just plug it all in your calculator. Kind of nice. A little bit convenient that way. Okay, number 4. Number 4 is a little tricky here. It says 3.5 squiggle coulombs. What the heck is this squiggle mean? Let's look in our reference table. That squiggle should look familiar. We talked about it a lot when we were doing friction in Unit 5. It was the symbol for the coefficient of friction. It was a mu. It was a mu, but we're not talking about friction here. We're talking about something else. So just like K is the electrostatic constant, but we also use that for the spring constant, mu is going to be this mu over here. Did you know it was hiding over there? What's that mean? It means micro. So just like you have a centimeter or a millimeter, you could have a micrometer. That's a tiny amount of length. Similarly, you could have a centicoulomb or a millicoulomb or a microcoulomb. So 10 to the negative 6 is micro. So if I said to you, I have positive 7 microcoulombs, that means I really have positive 7 times 10 to the negative 6 coulombs of charge. It's a tiny amount of charge. That's how you handle that. All right, so let's see what the problem looks like. We have positive 3.5 microcoulombs. So Q1 is equal to 3.5. The mu, the micro, means times 10 to the negative 6 coulombs. And Q2 is equal to negative 7.3 micro coulombs. It's experiencing attractive force. So the force is equal to negative 0.98 newtons. I actually didn't talk about that, why it's negative. Okay, so it says, what is their separation distance? What is R? And we also know K is equal to 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. Let me pause it for a second. What does this negative sign represent? Let's look at what we had for number 2. In number 2, we got a positive number for our force. And in number 2, there were 2 positive charges. So the electrostatic force was repulsive because they're like charges. They're going to repel each other. equal in magnitude, opposite in direction. Anytime you get a positive number for the force, positive means repulsive. Because even if you had a negative charge and another negative charge, a negative times a negative is a positive. All the other numbers are always going to be positive. You always have a positive distance, and you always have a positive electrostatic constant. So even if these two were negative, they're going to repel each other because negative repels negative, and you get a positive for the force. But what if one of them is positive and the other is negative? Opposites attract each other, and positive times a negative is a negative. So you're going to get a negative number for your electrostatic force. So negative means attractive. And this is just for the electrostatic force here. Okay, that's what this rule is for. It doesn't mean this particular charge by itself is going to repel everything. No, if this is a positive charge, it repels it. But if this is a negative charge, it's going to attract. So it's not for Q. Remember, with the Coulombs, this is the Q. This rule is for the force. All right, so let's look down here. They're telling you it's a negative force. So that's showing you the direction. Just like we in mechanics, the positive and the negative signs shows direction. Positive is up, north. Negative is down or south. Now we're talking about attraction or repulsion. So this shows that it's attractive, as we talked about before, and we can verify that because we have a positive charge and a negative charge. So yeah, they're going to attract each other. Okay, so that's the rule for that. It is important to know. All right, so what's their charge separation? Let's write down Coulomb's law. And I feel like solving for R first. So let's cross multiply. And we're solving for R, so divide both sides by FE. And then you take the square root of both sides. So R is equal to the square root of K times Q1 times Q2 divided by the electrostatic force. So now we could plug in our values. 8.99 times 10 to the 9 times 3.5 times 10 to the negative 6 times negative 7.3 times 10 to the negative 6 divided by the electrostatic force, negative 0.98. And you get an answer of, should I show it in your calculator? Let's see. Let me clear it. So the benefit of doing it this way is that I could just plug this whole thing into one line in my calculator. And you know me, I'm kind of lazy. I try to do as the smallest amount of work as possible. So let me make the calculator fit on the screen. And let's plug in the numbers here. So we're going to do the square root of, open parentheses for the numerator, 8.99 E9 times 3.5 E negative 6 times negative 7.3 E negative 6. Close the parentheses for the numerator, divided by, I like to put another set of parentheses for the denominator, negative 0.98. And that's just the electrostatic force. You don't have to square that, right? Because we're taking the square root for the radius. And that's all that she wrote. So you get 0.48, about a half a meter. 0.48 meters. So that was pretty easy. You just plug it in your calculator in one line. And as long as you're using the E button or you're super careful with your parentheses, if you don't use the E button, you have to put parentheses in around each scientific notation just to make sure that PEMDAS works. Then I think it's kind of easier to just do it in one line like that. Okay, number 5, kind of tricky. It says the diagram shows 3 small metal spheres with different charges. All right, so charge A is 10 coulombs, charge B is negative 10, charge C is 5 coulombs. It says compared to the force between spheres A and B, the force between spheres B and C is what? So okay, this is, let's see. Well, you're changing the coulombs and you're changing the distance. So let's set up our base case. Fe is equal to K Q1 Q2 over R squared. And from A to B to C, what happened to our radius? We started with 2, and then we went to 1. So we 1/2 our radius. I'll do it in blue like I did before. It's the same type of problem. You 1/2 the radius. Don't forget to square that. But what's happening to the coulombs? So at A and B, you had 10 coulombs and negative 10 coulombs. For B and C, you had 5 coulombs and negative 10 coulombs. So the negative 10 coulombs is the same for both, so we don't have to worry about that. So for this one, we had 10 coulombs for the charge. And for this one, we had 5 coulombs for the charge. So what happened from 10 to 5? What did we do? We decreased this by 1/2. So this is 1/2 is great. And Q2, you could even write Q2 stays the same. 1 times Q2. It doesn't change at all. So let's do the same thing we did before. We can't just start multiplying by things on one side of the equation and expect it to be equal. All right, in order to make it equal, we need to balance out the equation. So we put a 1/2 in the numerator on the right side. We better put a 1/2 in the numerator on the left side. In the denominator, we have a 1/2 that's being squared, and we said 1/2 squared is equal to 1/4. And now we have this super improper fraction, and you could do that keep, change, flip idea. So you keep this. You change this to multiplication. You flip the 1/4. So now you get 1 times 4. So that's 4. Over 2 times 1. So that's 2. 4 divided by 2 is equal to 2. So the electrostatic force is 2 times as great. Fe, 2 times Fe. So we're looking for twice as great. Okay. Number 6. It says the diagram below shows 2 metal spheres charged to 1 times 10 to the negative 6 and 3 times 10 to the negative 6 coulombs, respectively, on insulating stands separated by a distance of 0.1 meters. The spheres are touched together and then return to their original positions. So this is like in the previous homework, 10.3, it's law of conservation of charge. You want to find the total charge. So the total is equal to 1 microcoulomb plus 3 microcoulombs. I'm just being lazy. Micro is 10 to the negative 6, right? So Q total is equal to 4 times 10 to the negative 6 coulombs, or 4 microcoulombs. These are all positive. So that's the total charge for the system. When they're brought together, they're sharing that total charge. And this charge is spread out equally among both spheres. Then when you separate them, the charge is split equally between 2 spheres. So you have to divide it by 2, and you get positive 2 times 10 to the negative 6 coulombs on each sphere after the separation. So this becomes positive 2 times 10 to the negative 6. This becomes positive 2 times 10 to the negative 6. So as a result, so the spheres are touched together and return to their original positions. As a result, the magnitude of the electrostatic force between the spheres changes from 2.7 newtons to what? So this 2.7 newtons, they're basically telling you if you did Q1, Q2, and R squared, you get an answer of 2.7 newtons. But it's not going to be the same. It's a different magnitude. So you want to do Fe is equal to K Q1 Q2 over R squared. Fe is equal to 8.99 times 10 to the 9 times 2 times 10 to the negative 6. You could square it or do 2 times 10 to the negative 6 again, divided by R squared, so 0.1 squared. Don't forget to write your units, and you get an answer of about 3.6 newtons. So choice C. All right, that's it. Have a good day.